All right, welcome back, guys. So remember again, we're trying to think about this concept of chemical potential and how to predict chemical spontaneity. We said it's pretty simple for macroscopic things, and we said that we look at this potential energy. And so we said that there's the same thing going on in chemistry. There's a chemical potential. And so we want to identify what this chemical potential is and see how we can use it to determine chemical spontaneity. So there's a couple of different candidates you can start looking at to see if it determines spontaneity. And the first one you might think about is enthalpy, right? Is that what the chemical potential is? And so it is true that exothermic reactions are more likely to happen spontaneously. But there are a lot of exceptions. There's a lot of endothermic reactions that happen spontaneously, and there's a lot of exothermic reactions that don't happen spontaneously. So for example, ice melts as long as you're above 0 degrees Celsius spontaneously, right? So this is a spontaneous process and it's endothermic. So delta H is not enough. Enthalpy is not enough to predict spontaneity. It's not enough to, meet our demands for this chemical potential value. So let's take a look at examples when delta H is 0 and see what else is going on in the system. So what about when delta H is equal to 0? So when delta H is equal to 0, the whole system does not change in terms of heat, right? So for example, if we have a hot block and a cold block, so we'll call this hot, we'll call this cold, and there's in some kind of vacuum where they're going to exchange heat, but no other heat is going to be lost to the environment. So what we'd end up with is some kind of temperature in between. And so we've done no work in this system, right? So work is 0, and the change in H of the system is 0, right? So if we're thinking of the system as both of these blocks, it's 0, right? One of them has lost heat, one of them has gained heat, but overall, if you think of both of these two as the system, there's no change in delta H. But what did happen and what did spontaneously happen is that energy was dispersed. So energy is dispersed evenly between these two blocks. So that happens spontaneously, even though this is, not occurring with a change in delta H, right? So if we're going in kind of this direction over here, if we're going from left to right, we say this is spontaneous, right? So energy is spread out spontaneously. But what about the reverse? Will the reverse ever happen? Will you ever have some kind of two blocks connected that are at the same temperature, and then one's going to become hot, another one's going to be cold? And the answer is no. That's not going to happen spontaneously. So for example, if you leave your hot pizza out on the counter, it's going to cool to room temperature. That'll be a spontaneous process. But the pizza will not suddenly start to get hot spontaneously. That's not going to happen. And the pizza is not going to get colder than the room temperature. That's not going to happen. So we can see that this energy dispersion seems to have some kind of connection with spontaneity. Let's take a look at another example. Let's say in this example, you have this kind of thing right here, and it's filled with gases, and these gases are in a vacuum, right? So on one side, you have, gas A, and then on the other side, you have gas B. And let's say this was, closed before, and then let's take a look at what happens when you open it. So when you open it, these two gases will indeed mix, right? So gas A and gas B will mix with one another. And so you'll have a mixture of gases. And as soon as you open that stopcock, this will happen spontaneously. This is indeed a spontaneous process. But if you just let this gas sit over here, will it ever reseparate? Will the gases ever reseparate? So you have all of gas A on one side and all of gas B on the other side? And the answer to that is no. So this is a non-spontaneous process. And again, here, the delta H is equal to 0. We haven't exchanged any heat, assuming these two gases were at the same temperature at the beginning. There's been no work done because we're in a vacuum, and so there's no change in enthalpy, right? But again, just like before, energy was dispersed. Here, matter is dispersed. So we can see when we have no change in enthalpy that this dispersion seems to be a driver of spontaneity, where things want to go to the more dispersed state and not go towards the less dispersed state. And so same picture here I have for you. That beeping is annoying. People keep sending me too many emails. All right, so as you can see, right, same example as before. This one, in the top one, the gases aren't mixing. It's just you're opening and the gas is going to disperse, right? So one direction is going to be spontaneous, the other direction is non-spontaneous. This example, same thing. When these two hot blocks join together, they'll spontaneously get to the same temperature, but going backwards is not going to happen, right? This will be a non-spontaneous type of process. And so, again, in both of these examples, stuff has been dispersed, whether that be energy or matter. And so what we call this dispersion is entropy. 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 And it gets the symbol S. So we have enthalpy, which is kind of talking about heat, and we have entropy, which has this symbol. And so both of these examples, entropy has increased. And we'll get to the strict definition in a bit here. But for now, we're just going to say that entropy is related to disorder / randomness / dispersal. Dispersion, I guess. Right, so things want to get towards a more disordered state, a more random state, a more dispersed state, right? These gases don't want to be all organized in one side. They want to be randomly floating around in both sides. So just some more examples of things where entropy has increased. So in this first example, we have water in the form of solid ice melting into liquid water. And so in ice and a solid, molecules are not allowed to move. In a liquid, they can move around. So you can see from no movement to being able to move, that's an increase in entropy, right? The matter has dispersed. Same thing for when we go from a liquid to a gas, we're increasing the amount of entropy here. We're dispersing our matter, dispersing our energy in a more wide area. So we're increasing the amount of entropy. And same thing when we dissolve something. So when we looked at solutions, we said that even solutions that have a delta H of 0 or even a positive delta H can still occur. And we said it was because of entropy. And so here you can see you have a nice ordered system, right, of positive, negative charge. And then here you have a more random, a more disordered system where your matter and your energy are more dispersed throughout the system, an increase in entropy. So let's give it the strict definition and take a look at it. So entropy, again, gets the symbol S. And so the strict definition here is that entropy is a thermodynamical function that increases with the number of energy equivalent ways to arrange the components of a system to achieve a particular state. So let me go ahead and write that all down because it was a mouthful. So thermodynamic state, thermodynamic function that increases with the number of energy equivalent ways to arrange the components of a system to achieve a particular state, right? Energy equivalent ways to arrange a particular state. So the more ways you can arrange a system to still achieve a particular state, the more entropy it has. And so it gets this formal equation of S equals K ln W. So let's go through this piece by piece, right? We just said S was entropy. This K is a constant, and it's the Boltzmann constant. So it has nothing to do with the K from the kinetics or the equilibria. This is a separate K. There's a lot of Ks, get over it, right? Not K from kinetics / equilibrium. It's its own thing, its own separate K. It has a value of 1.38 times 10 to the negative 23 joules per Kelvin. And you can see, you can check out your book how they derive that. This ln is a math thing, right? It's the natural log. So it's log base E. Again, you can look in your math textbook or in your chemistry textbook, and it'll explain it more in depth. And then here, W, right? W is this number of energy equivalent ways to arrange the components of a system to achieve a particular state, right? So number of energy equivalent ways to arrange a system, right? So the S we just learned is entropy. K is just a constant. Natural log is just a mathematical function. W, let's take a look at W, this number of energy equivalent ways to arrange a system. And so in order to talk about W, we have to talk about things called macro states versus things called micro states. And so the macro state is the big picture that you're looking at. So this is the overall state, right? And this state can be described by macroscopic properties such as pressure, temperature, volume, that kind of thing. So pressure, temperature, volume, that kind of things. They're what describe the macro state. You know, this pizza is at 35 degrees Celsius. This gas has a volume of this. It has a pressure of this. The microstates are the distribution of energy / matter at any instant, right? So it's a distribution at any instant. So if you had, a bunch of, if you had a balloon filled with gas molecules, the pressure of that system is the macro state. And then when you look at the micro state, maybe one of the molecules is here or here or here. That's one microstate. Maybe in a different microstate, they're kind of over here, but the pressure is the same. And so overall, the macro state is made up of many microstates. So a macro state is made of many micro states. And we'll take a look at exactly what that means right now. So, for example, let's say you have 4 particles, and we'll call them A, B, C, D, in 2 boxes with a hole in between. Right, so these particles are free to move around between the 2 boxes. And so we can think about what the macro states are and what the micro states are. So let's take a look at the macro states first. So the macro states are describing the property. So you can think about this as a balloon, and the number of molecules is proportional to the pressure of the balloon, or you can just think about where they're at type of thing, right? So let's take a look. In one of our macro states, we could have all 4 particles in one box. In another macro state, we could have 3 on the left, 1 on the right, Another microstate would be 2 on each side. Yet another microstate would be 1 on the left, 3 on the right. And then the final microstate would be all 4 of your particles on the right. So we'll call this 1, 2, 3, 4, 5, right? And so one of the things we kind of want to ask ourselves is which one of these macrostates is most likely to occur? So which macrostate is most likely to occur? And in order to answer this question, we have to look at the microstates. So pretend, you're a gambler, you're gambling on here, you put down $1,000 or something, and you have to pick one of these and say, which one of these is the most likely to occur? Which one is the most likely to occur? So you have to look at the different combinations in which they could occur. So for example, right, so we'll call this side the microstates. A little too close to each other, but whatever. We'll take a look at this as the microstates. The only way all 4 particles are on the left side is if all 4 particles are on the left side, obviously, right? So A, B, C, and D, they all have to be on the left side in order to achieve this macrostate. That's the only way you can organize it. If we take a look at the next micro or macro state, we have 3 on the left, 1 on the right. Well, there's a number of different combinations you can do to achieve that. So for example, maybe it's particle D that is on the right while the other 3 are on the left. Or maybe it's particle C that's on the right. Or maybe it's particle B that's on the right. Or maybe it's particle A that's on the right. So you can see all 4 of these combinations give the same macrostate. All 4 of these microstates have the same macrostate. They're all 3 on the left, 1 on the right. So you can see that this macrostate right here has 4 different microstates, whereas this top macrostate only has 1 microstate. And so you could repeat, keep going on and on, right? How could you describe this macrostate in terms of microstates? Well, you could have 2 on the left, 2 on the right. I'm not going to write out all the other combos, so there's 5 other combos for a total of 6. So there's 6 total ways you could combo these guys up here. And then if you think about number 4 over here, it's going to be the same as number 2 except reverse, right? Instead of 3 on the left, 1 on the right, you've got 3 on the right, 1 on the left. And same thing for microstate, for the microstates for macrostate 5, right? All 4 are going to be on the right side. So here you'll have 4 combos. You have 1 combo, right? So since we know that S is equal to K, ln W, and we said W here was the number of microstates, which one of these has the largest entropy? And so if you plug the numbers in, what you'll see is that higher W equals higher S. And so number 3 has the highest entropy. Followed by 2 and number 4, and then 5 and 1, right? So the more ways you can arrange your macro state, the more microstates you have. The more microstates you have, the more entropy your system has. And so this is shown also, same thing here, just copied it from the book. This is shown right here, same thing I drew up there. You can see all the different combinations. This time they colored them instead of saying letters, but you can see that the third state with 2 on each side has the highest number of microstates and thus the highest amount of entropy. And so if you actually take a look at this picture right here, and then you kind of turn it sideways, And if you think about it as a graph, it kind of looks like a probability curve, right? It looks like a probability curve. So if you were gambling and you'd say which macro state is most likely to happen, your best bet would be go with number 3, right? You could make some money if the other person didn't know that. So when we're talking about entropy, what we're talking about is which state is most likely to happen from a statistical point of view. And when we're talking about that, we're talking about which one has the most amount of microstates. Which uh, which state can you organize in the most amount of ways, right? So if you're looking at a change of S, you're talking about K, ln, Wf minus Wi, right? Where this is final number of macro states. And then this one is right here, initial. So let's say if your kind of Wf is greater than your Wi, so maybe you're going from, macro state 1 to macro state 3, you would then have a positive delta S. If Wi is less than Wf, other way around. Wf is less than Wi, maybe you're going from, macro state 3 to 1, you have a delta S that's negative. That's negative, right? You're going to a less likely scenario. And as we saw from our previous examples of this kind of heat and this gas dispersing, generally you want to have a positive amount of entropy. Systems want to tend towards more disorder, not less disorder. And then when you're thinking about this curve right here, what you're talking about, the number of possibilities is 2 to the n, where n is the number of particles, 2 is the number of boxes. And so although here there's only kind of 5 different macro states and only 16 different micro states, if you raise it up to, like, say 2 up to 1 mole, like if you had 1 mole of particles, it'd be 2 to the 6.02 times 10 to the 23rd, right? And so then you could calculate the chance that all of the gas molecules end up on one side. There'd only be 1 microstate for that. You could actually calculate the chance that happens. So chance all gas ends up on the same side. If you do the calculations, you'll get approximately 1.7 times 10 to the negative 22%. Right? So the chances that 1 mole of gas dispersed between kind of 2 boxes, the chance that all of those gas molecules will end up on one side is extremely, extremely, extremely tiny from a probability point of view. And entropy is very much so related to that. So that's kind of talking about dispersion of matter. Dispersion of energy, it's the same analogy. You can take a look at your OpenStax book and read through there, but it's essentially the same thing, except instead of talking about a molecule moving, you're talking about kind of a packet of energy moving, right? So I'll leave this picture here. You can look into your book, but it's basically similar for heat / temperature, right? So in general, things want to be more dispersed because that gives them a larger number of microstates, which makes it more probable that that will occur, right? So again, positive delta S, that means that the system gained entropy and it got more disordered or more dispersed. Right, and then a negative delta S would be the system lost entropy or it got more ordered. Right, things want to spread out. They want to become more disordered, right? So what we're looking at here is the sign of delta S. So the most common example when you're going from a solid to a liquid to a gas to phase transition, when we're going left to right, we're spreading out not only our matter, but our energy, right? Solids can't move at all, so they can't cover much ground. Liquids are allowed to roll one another, so you've dispersed the amount of matter and energy there. And then finally, gases are allowed to fly all over the place, so they've got the most disorder, the most entropy. So going left to right, you gain disorder, and so it's a positive delta S. And then going from right to left, you lose disorder, or you become more ordered, whichever way you want to say it. You have a negative delta S. Same thing what this picture shows. And you can think of it in terms of microstates as well. You're a crystalline solid. The molecules can't move from one another, so there's not many ways you could arrange this macro state of a crystalline solid. Whereas a liquid, they're allowed to roll one another, so you could swap these guys out and achieve different microstates for the same macro states. And same thing for gas molecules. Maybe at one microstate, the gas molecule is here. Maybe at a different microstate, it moves a little bit and is here now. So again, increased microstates, increased disorder, increased amount of entropy. So kind of same thing here, same picture here. Let's take a look at this picture on this right here first, then we'll move on to the one on the left. So here it plots entropy as a function of temperature, right? So you can see even when you're heating something, the entropy is indeed increasing. Even before the phase transition, your entropy is increasing. That's because you're giving your molecules more energy. And so in the case for a solid, they're allowed to vibrate more. And so they can vibrate into kind of new places, and you can disperse that energy further. But you can see during phase transition, there's a massive amount of increase in entropy. And again, that makes sense because the molecules are more dispersed. And we'll see another example of that in a minute here. And then same thing here, why is entropy kind of increasing when we don't have a phase change? You can kind of think back to CHEM101 in these temperature curves, right? So this is T1 and T2, so temperature 2 is higher than T1, so this is kind of hot, and this is cold, right? And so this is the kinetic energy of the molecules and the number of molecules in there. So you can see you don't have a whole lot of molecules. You don't have a whole lot of molecules with a lot of energy, right? You've got a couple molecules with a lot of energy, and then most molecules without any energy. Whereas this one right here, you can see this curve is flattened. So it's more dispersed. The energy throughout the molecule is more dispersed. It's more disordered, and so you have a higher amount of entropy. So when you increase temperature, you increase the amount of entropy. When you have a phase transition, you increase the amount of entropy as well. This picture right here is a really good description of kind of another reason why phase changes have a large increase in entropy. So you can think about this phase change as gaining additional places for this energy to be. So for example, in this solid right here, all these molecules can do is just vibrate back and forth. All they can do is vibrate back and forth. That's the only way they can kind of disperse their energy. Whereas gases over here, they can have translational motion, so they can move around, they can disperse energy that way, they can rotate, they can spin around, they can disperse energy that way as well. So again, when you have a phase transition, think about kind of what ways can you organize this? How many microstates do you have? Do you have more? Do you have less? And then you can see whether your state is increasing or decreasing in entropy. So let's take a look at a quick little exercise, sign of delta S. So go ahead and predict for all of these things what the sign of delta S is going to be. So I'll write them down. You want to go ahead, pause the video once I'm done here, and then try to figure them out yourself. So again, pause the video, take a look, and let's figure these out. All right, so I'm assuming you paused the video and took a look at this. So just a small error here. This should be gas. This should be liquid, right? So when we're going from a gas to a liquid here, that's our example. Kind of going this way, right? We're going from a gas to a liquid, so we can see we have a decrease in the amount of entropy. Our system is getting more ordered, right? It's shown in this picture as well. So our system is getting more ordered, so we've got a loss of entropy, and so overall this would be a negative amount of entropy. Right, so again, gas to liquid, negative amount of entropy. When CO2 is subliming, what you're talking about is going from a solid to a gas. Again, we just learned gas has more amount of entropy, so we're going to increase the amount of entropy. In this next one, we've got gas turning into gas. So you might think, okay, that's about the same, but think about how much gas you have here. Here you have 2 gas molecules turning into 3 gas molecules. Well, the more gas molecules you have, the more ways you can organize an energy equivalent system, more microstates, more entropy. So this ends up being positive. This next one, when we're increasing temperature, we've already seen that that is indeed an increase of entropy. You can see that from these plots right here or from this curve right here as well. Both of those demonstrate that point pretty well, right? But whoops, that should have been down here. And then this boiling again is a liquid to a gas, so that's going to be a positive increase of entropy. So here we're going from silver plus and chloride minus to a solid, right? So you have to kind of assume that these are aqueous solutions, and so they're floating around by themselves, and now they're forced to be together, forced to be in a packed solid. Well, we learned that dissolving increases entropy, so precipitation must be the opposite, and so this is a decrease in entropy. The system is indeed getting more ordered. Before, you could have these silver and chloride particles floating around wherever they want to be, and then after, you've got them trapped inside of this solid. All right, so this next one is probably kind of the trickiest thing. So you're looking at this guy, you're saying, okay, there's a whole bunch of stuff happening here, but I've got kind of 17 things going into kind of, write that down. Yeah, okay, that's not gonna be a good example. So we have kind of liquids here, and we have gases here, and we have gases here. And so if we think about what has more entropy, well, a gas has significantly more entropy than a liquid. So really what you kind of want to pay attention to here is the amount of gas molecule you have, right? So here overall you have 17 kind of things turning into 18 things. And you might think, oh, it's got to gain entropy because it's dispersing into more things. More things is more entropy. However, when we take a look at how much gas, here you've got 15 gas turning into only 12 gases. And since gases have much more entropy, this reduction in the amount of gas is going to be overpower your increase in the amount of things. And so at the end of the day, this will actually have a negative amount of entropy. It will lose entropy because your system is becoming more ordered because you are losing the most disordered thing, which is the gas. So take a look at your homework. For some more examples, I'll do like a video homework thing with more examples. Get comfortable with it. It's not too bad. You just kind of want to think about, is my stuff dispersing? Do I have more stuff with more entropy? That sort of thing.